The Milky Way is not a perfect river of light. Look closer, and you will see ragged patches of pure blackness, like holes punched in the starry fabric. Those are not empty voids. They are dark nebulae, colossal clouds of cosmic soot so thick they swallow starlight whole. They are the universe's greatest hiding places, concealing secrets about the birth of stars, the shape of galaxies, and the raw materials of reality itself. This is a cosmic detective story, and we are exploring 25 of these enigmatic shadows. You will gain a new understanding of the galaxy's hidden architecture, the forces that build stars, and the profound mysteries written in dust. What strange shapes are being sculpted in those Inkai depths right now, and what might they tell us about our own sun's forgotten origins? One of the most prominent ink stains on the sky is the Coalsack Nebula. For anyone in the southern hemisphere, it is an unmistakable feature, a deep, starless void nestled right beside the brilliant stars of the Southern Cross. It is so prominent that early European explorers like Amerigo Vespucci documented it in their logs, calling it the Dark Canopus, a strange blackness where the heavens seemed to simply end. This was not a hole, but a clue. The Coalsack is a vast, nearby cloud of interstellar dust, a floating mountain range of carbon and silicate grains finer than smoke, but so extensive it completely blocks the light from the countless stars that lie beyond it. Think of it as a cosmic curtain drawn across a brilliant stage. We are sitting in the front row, and this thick, dark velvet is all we can see. Its very prominence in our sky is a testament to its relative closeness, a mere 600 light-years away, which is practically next door in galactic terms. Yet this proximity raises a profound question. What cosmic event caused this immense cloud to gather here, in this particular patch of space, and why has it not yet collapsed to birth a new cluster of stars? Its stark, isolated silhouette against the Milky Way suggests a story paused, a frozen moment in a process we are only beginning to understand. What force is holding this colossal sack of star stuff in suspense? While the Coalsack is a sprawling dark blanket, other nebulae carve intricate shapes from the light. Perhaps no silhouette is more famous or haunting than the Horsehead Nebula. That iconic profile, a knight in a cosmic chess game set against a brilliant red backdrop, is instantly recognizable, but this is not a standalone object. It is a towering pillar of cold, dense gas and dust, a protruding cape of the much larger Orion B molecular cloud, over 1,000 light-years away. The vibrant red canvas behind it, known as IC 434, is a vast region of hydrogen gas, excited to a crimson glow by the fierce ultraviolet radiation from a nearby star. The Horsehead itself is a dark fortress against that storm. Its famous shape is being actively sculpted by that same stellar radiation, a process astronomers call photoevaporation. Think of it as a cosmic ice sculpture under a blazing sun. The intense light and stellar winds are slowly boiling away the less dense material, eroding the nebula and defining its sharp edges. This raises a poignant temporal question. We are witnessing a fleeting masterpiece. How long will this majestic shape endure? Estimates suggest it may lose its defining form in another 5 million years, a blink in cosmic time. Yet within its dark, dense core, shielded from the harsh external radiation, conditions might be perfect for a different story. The very pressure from the surrounding erosion could be triggering the collapse of gas clouds, sparking the birth of new stars deep inside its shadowy heart. What celestial nurseries are operating in secret within that famous silhouette, completely hidden from our admiring gaze? The delicate erosion of the Horsehead shows dark nebulae as temporary sculptures, but others reveal the hidden architecture of the galaxy itself. Slithering through the rich star fields of the constellation Ophiuchus is a different kind of shadow, a dark nebula catalogued as Barnard 72 but far better known as the Snake Nebula. Its form is unmistakable, a long, sinuous and twisting ribbon of absolute blackness set against a dense backdrop of distant stars. It does not look like a simple blotch or a ragged hole. It looks intentional, like a cosmic serpent carefully placed upon the sky. This is not a lone cloud. It is part of a vast, interconnected complex of dark nebulae in this region, a sprawling network of cold gas and dust known as the Ophiuchus Dark Cloud Complex. The snake is one of its most distinct and isolated filaments. Its very existence, with that remarkably clean, curved, and coherent shape, forces a question upon us. In the chaotic, turbulent environment of interstellar space, where random motions and collisions should tear such delicate structures apart, how does a perfect serpent form and persist? The answer seems to lie in invisible forces shaping the cosmos. Astronomers studying structures like the snake believe its morphology is a direct imprint of the galaxy's magnetic field. Imagine the dust and gas within the cloud as countless tiny, magnetically sensitive particles. As the cloud evolves, these particles can align along the lines of the galactic magnetic field, much like iron filings lining up on a piece of paper held over a magnet. This alignment, combined with the slow, swirling motions of turbulence within the cloud, can stretch and sculpt the material into these long, filamentary threads. The snake, then, is not just a dark cloud, it is a cosmic windsock, revealing the direction and influence of magnetic forces we cannot see. But these filaments are more than just magnetic tracers, they are potentially fundamental to star formation. Dense knots often form along these dark threads like beads on a string, and within those knots, gravity can overcome all other forces. This leads to a compelling idea that the universe may preferentially build stars, especially smaller, sun-like stars, within these intricate filaments of darkness. Is the Snake Nebula quietly cradling the seeds of new solar systems within its inky body? Its silent, coiled form may be a blueprint for creation. That magnetic blueprint of creation stretches across the sky in even grander forms. Rising from the star-rich plain of the Milky Way in the direction of the constellation Sagittarius is one of the largest and most recognizable silhouettes visible from Earth, the Pipe Nebula. To the naked eye under a truly dark sky, it appears exactly as its name suggests, a celestial pipe with a long, straight stem and a rounded bowl, seemingly carved from the very starry background. This is not a single object, but a sprawling complex of several distinct dark nebulae, catalogued by astronomer Edward Emerson Barnard as numbers 59, 65, 66, 67, and 78. Together, they sketch this familiar shape against the brilliant backdrop of our galaxy's central bulge. The scale is almost incomprehensible. The stem of the pipe alone stretches over 7 degrees across the sky, which is the equivalent of 14 full moons placed end to end. In physical terms, this translates to a structure hundreds of light years long. Its location is no accident. The Pipe Nebula forms the most prominent part of an even vaster dark cloud complex known informally as the Dark Horse or Great Dark Horse. This colossal shadowy figure, which some observers see as a prancing horse, acts as a dramatic foreground curtain, and what lies behind that curtain? The very heart of our galaxy. The Pipe and the Dark Horse complex sit directly along our line of sight to the Milky Way's bustling, densely packed core. This positioning creates a profound observational puzzle and a tantalizing opportunity. We are looking at a three-dimensional scene flattened into a two-dimensional picture. Which parts of this dark complex are relatively nearby clouds, and which are distant, towering walls of dust that actually block our view of the galactic center? Disentangling this cosmic depth perception is a major challenge. The sheer amount of material in the Pipe Nebula is staggering. Astronomers estimate its mass could be many tens of thousands of times that of our own sun, all in the form of that cold, dark gas and dust. This immediately raises a compelling question. With that much raw star-making material gathered in one place, what is happening inside? Optical telescopes see only an impenetrable blackness, but that is just the beginning of the story. The dust itself, while blocking visible light, glows faintly with heat in the infrared part of the spectrum. Space-based infrared telescopes peer straight through the soot, revealing a hidden landscape. Within the bowl of the pipe, for instance, astronomers have discovered embedded clusters of newborn stars, their faint light once completely trapped by the surrounding cocoon. The nebula is not a static sculpture, it is an active, if shrouded, stellar nursery. How many more of these infant stars are still veiled? And what does the specific arrangement of this dark pipe tell us about the flow of material toward the most chaotic and energetic region of our entire galaxy? Far from the galactic center, another serpentine shadow glides through a quieter part of the southern sky. In the small constellation of Musca, the Fly, lies a dark nebula with a wonderfully peculiar name, the Dark Doodad. This nickname, coined by amateur astronomers, perfectly captures its appearance, a long, whimsical scribble of cosmic dust. It is not a blot or a hole, but a distinct, slender filament, a dark river of soot stretching for over 3 degrees. That is the width of 6 full moons placed in a row, a significant structure considering its location well away from the Milky Way's crowded plain. This relative isolation is a gift to observers. Without a dense backdrop of bright stars to confuse the view, the dark doodad stands out with remarkable clarity, offering an almost textbook view of a dark nebula's anatomy. We can trace its contours, note its subtle knots and variations in density, and appreciate it as a distinct astronomical object rather than just an absence of light. Its proximity at roughly 700 light-years away makes this detailed study possible. We are looking at a nearby structure with a front-row seat to its intricate form. And that form is the first clue to a deeper mystery. The dark doodad is remarkably straight and coherent over an immense distance. In the turbulent interstellar medium, such clean, linear structures do not form by accident. This leads astronomers to a compelling hypothesis that the doodad may be a surviving fragment of a much larger shell. Imagine a gigantic, ancient bubble of gas, blown by the winds of long-dead massive stars, or perhaps even a prehistoric supernova explosion. As this bubble expanded and aged, its walls fragmented and dissipated. The dark doodad could be one of the largest remaining pieces of that wall, a fossilized ridge of dust that has maintained its integrity while the rest of the structure vanished. What titanic event in our galactic neighborhood left this dark scar as its only memorial? The nebula's pristine visibility also makes it a perfect laboratory for studying the dust itself. By analyzing how it dims and reddens the light of the stars that are actually behind it, astronomers can deduce the size, composition, and distribution of the individual dust grains within the cloud. These are the fundamental building blocks of future planets, and the dark doodad offers a rare, clean sample to examine. For amateur astronomers with modest telescopes under dark southern skies, finding this dark river is a special thrill, a chance to see a cosmic process frozen in a simple, elegant line. But that simplicity is deceptive. Its very existence asks how such delicate order emerges from the chaos of space, and what forgotten violence shaped this quiet doodad on the celestial canvas. The delicate filaments of the dark doodad show structure on a grand scale, but sometimes the most profound questions are contained within the smallest, simplest shapes. Against the starry backdrop near the constellation Ophiuchus lies a perfect, circular patch of nothing. It is called Barnard 68, and it looks less like a cloud and more like a hole someone has punched clean through the fabric of the night sky. Its edges are impossibly sharp, a stark, ink-black disk set against the dense star field behind it. This is no sprawling complex or wispy filament. Barnard 68 is the textbook example of a Bok globule, a small, isolated, and incredibly dense pocket of gas and dust. Its near-perfect spherical shape is a clue to its nature and its future. This is a cloud in profound suspense, holding itself together against the inevitable pull of gravity. For decades, optical telescopes could only tell us what it blocked, not what it was. The breakthrough came when we learned to see with different eyes. Infrared and radio telescopes can peer straight through the soot, reading the faint heat signature of the dust and the molecular whispers from within. What they revealed transformed this simple black spot into a cosmic laboratory. Barnard 68 is not just a cloud, it is a cold, dense core, a singular lump of interstellar material with a temperature only about 10 degrees above absolute zero. The pressure from the outside of our galaxy is actually squeezing it, and its own gravity is pulling it inexorably inward. We are catching it in a fleeting, precious state, a state of near collapse. This raises two fundamental and beautiful questions. First, is this single, isolated sphere destined to become a single star, perhaps with its own family of planets? It contains enough material for a small stellar system, and its isolation means it will likely evolve alone, without the chaotic influence of neighboring star births. Second, what is the final trigger? What tiny, imperceptible nudge, a passing shockwave from a distant star, a subtle increase in density from within, or simply the slow, relentless accumulation of mass will be the last straw that causes this sphere to suddenly give way and begin its fiery transformation? Barnard 68 is a frozen moment, a cosmic breath held. Studying it is like watching a single raindrop on a window pane, knowing it is just about to fall, and trying to understand the exact physics of that final release. In its perfect, dark simplicity, it holds the blueprint for the birth of a sun. The perfect, suspended sphere of Barnard 68 shows a nebula in waiting, but other dark structures are caught in a far more violent and creative act. In the constellation Monoceros, embedded within a sparkling group of stars nicknamed the Christmas Tree Cluster, stands a monument to cosmic conflict, the Coalsack Nebula. This is not a subtle shadow or a delicate filament. It is a stark, towering pillar, a dark spearhead 7 light-years long that points directly away from the brilliant heart of the cluster. Its shape is no accident. It is the direct result of an ongoing assault. At the center of the Christmas tree cluster burns a group of tremendously hot, massive, and young stars. Their fury is unleashed in the form of searing ultraviolet radiation and supersonic stellar winds, a relentless torrent of energy that blasts outward into the surrounding molecular cloud from which the stars themselves were born. The Coalsack Nebula is what remains of that cloud, a dense, resilient fortress of gas and dust that has so far withstood the onslaught. The brilliant rim you see at its edges is not the nebula itself glowing, but the wall of the fortress under direct siege. The intense ultraviolet radiation from the massive stars is ionizing the gas at the very surface of the dark pillar, stripping electrons from atoms and causing it to fluoresce with a faint, eerie light, like a neon sign etched in space. This bright rim is a shock front, the visible boundary between the destructive power of starlight and the stubborn resistance of cold, dark matter. But this is not merely a story of destruction. The same radiation and winds that are evaporating the pillar are also compressing it. Imagine a sculptor not with a chisel, but with a blowtorch. The intense pressure from the outside is pushing inward on the dense knots of material deep within the pillar's shadowy interior. This compression can trigger a second wave of star formation, a cosmic chain reaction where the death of one part of a cloud gives birth to new stars in another. This raises two profound questions about the cone's hidden depths. First, what is growing inside that dark spire? Infrared telescopes have indeed detected several very young stellar objects, protostars still wrapped in their dusty cocoons, hidden safely behind the dark wall that shields them from the very radiation that helped create them. Second, how does this brutal erosion process affect what kind of stars form? The theory is that this external triggering might favor the creation of lower mass stars like our Sun, as the compression breaks the cloud into smaller, denser fragments. The Cone Nebula stands as a perfect case study, a frozen moment in a cycle of chaos and creation. It asks us to consider whether the most fertile stellar nurseries are not the quiet, dark corners of space, but the turbulent, irradiated frontiers where light itself carves new worlds from the darkness. But that fierce sculpting of the Cone Nebula is not a unique event. Far across the galaxy, another monumental pillar rises from a sea of glowing gas, its form so familiar it has earned the name the Elephant's Trunk Nebula. This colossal structure, officially catalogued as IC 1396A, is a dark river of dust snaking through the heart of a vast, bright-emission nebula in the constellation Cepheus. From our perspective, the shape is unmistakable, a cosmic proboscis over 20 light-years long, reaching out into space as if searching for something. The entire scene is illuminated and defined by a single, brilliant actor, a massive young star named HD 206267. This star is the powerhouse of the region, its intense ultraviolet radiation flooding the surrounding cloud, causing it to glow with a soft red hue. The elephant's trunk itself is a dense, cold fortress within that radiant storm. Its iconic shape is carved by the same brutal physics we saw at the cone. The side facing the brilliant star is bathed in that erosive light, creating a bright, ionized rim that traces the trunk's silhouette like a neon outline. This rim is a shock front, a wall where the star's energy meets the nebula's resistance. Yet within the deep, protective shadows cast by that wall, a different story unfolds. The trunk is not just being destroyed, it is giving birth. The immense external pressure from the stellar radiation is compressing the gas and dust inside the pillar, triggering gravitational collapse in several dense knots. Infrared and radio observations have confirmed the presence of multiple young stellar objects embedded within the dark material, protostars still drawing in matter from their dusty womb. This creates a breathtaking cosmic balancing act. On one side, gravity pulls the material inward, trying to form stars. On the other, the radiation from the massive central star pushes outward, trying to blast the pillar apart. The elephant's trunk is the visible line where these two titanic forces are locked in a temporary stalemate. This raises urgent questions about the fragility of such beauty. How stable is this structure, really? The pillar is undoubtedly being evaporated, its material slowly stripped away and ionized. The young stars forming inside will eventually ignite their own stellar winds, which will further contribute to the destruction of their own cradle. We are witnessing a transient masterpiece, a structure that may only exist for a few million years. Does the shape we see today, that perfect elephantine curve, represent a moment of near equilibrium, or are we catching it just as it begins to fray and dissolve? The trunk forces us to consider the timescales of creation and destruction in the universe, and how often the most fertile places for new life are also the most violently unstable. Sometimes the universe places its evidence side by side for us to see. In the constellation Sagittarius, a telescope reveals one of the most dramatic contrasts in the night sky. On one side, a brilliant, compact jewel box of stars known as the Open Cluster NGC 6520. Hundreds of young, hot suns sparkle together in a loose gathering. And pressed right up against it, a blot of such profound blackness it looks like a drop of ink spilled on a diamond necklace. This is Barnard 86, the ink spot nebula. The pairing is no mere optical illusion. These two objects are physically linked, separated by only a few tens of light years and moving through space together. The brilliant cluster is young, its stars likely only around 150 million years old. The dark nebula beside it is the ghost of its past. Barnard 86 is almost certainly the last remaining dense fragment of the vast molecular cloud that collapsed to form NGC 6520. Think of it as the empty, torn cocoon left behind after the butterflies have emerged. This raises a fascinating question about efficiency. When a cloud gives birth to stars, not all of its material gets used. The most massive, energetic stars that form first unleash powerful winds and radiation that begin to violently blow away the very cloud that created them. This process, called feedback, can shut down star formation prematurely, dispersing the remaining gas and dust into space. The ink spot presents us with a snapshot of this dispersal nearly complete. The sparkling cluster has done its work, carving out a cavity and evaporating most of its cradle. Barnard 86 is what remains, a stubborn, dense knot that somehow survived the stellar hurricane. But its days are numbered. The radiation from the nearby cluster is slowly eroding it, stripping away molecules atom by atom. How long can this dark fragment hold out, and what does its current mass tell us about how much raw material was wasted, never becoming part of a star or planet? This beautiful, stark contrast is a direct lesson in cosmic economics, showing us that even in creation there is debris, and that the most luminous beginnings often cast the deepest shadows. That stark contrast between light and dark is writ large across our entire sky. The most profound dark feature visible from Earth is not a single nebula, but a colossal tear in the fabric of the Milky Way. Gaze upward on a clear summer night, and you will see it, a great branching river of blackness that splits the luminous band of our galaxy in two, stretching from the constellation Cygnus in the north all the way down to the rich star clouds of Sagittarius. This is the Great Rift. For millennia, human cultures have woven this dark division into their mythologies, seeing it as a celestial serpent, a road of souls, or a great crack in the heavens. Early Western astronomers, lacking an understanding of interstellar dust, often interpreted it more literally as a vast, empty channel through the stars, a true rift in the structure of the galaxy itself. We now know it is neither a crack nor a channel. The Great Rift is a monumental, three-dimensional landscape of dark nebulae. It is not one object, but a series of overlapping foreground dust clouds within our own spiral arm, the Orion Spur. We are embedded within this complex, and as we look along the plane of the Milky Way, our line of sight passes through countless dense clouds of this cosmic soot. They blot out the light from the billions of stars that lie beyond, creating the illusion of a yawning chasm. This positioning creates one of the greatest observational challenges in astronomy. The Great Rift acts as a towering, opaque curtain hung directly between us and the most interesting place in our galaxy, the Galactic Center. In visible light, we are essentially blind to our own galaxy's bustling core. This profound obscuration forced a fundamental question for centuries. What is the true nature and structure of the Milky Way's heart? It was like trying to map the skyline of a distant city while standing in a dense, perpetual fog. The breakthrough came when we learned to see in other wavelengths. Radio waves and infrared light can pierce through the dust of the Great Rift as if it were not even there. These new eyes revealed the shocking truth that our galaxy has a brilliant, compact core, harboring a supermassive black hole and surrounded by a frenetic swarm of stars. The Great Rift had been hiding the most dramatic part of our cosmic home, yet this obscuring curtain is not a barren wall. Within its dark folds, the same processes of creation we have seen elsewhere are at work. Parts of the Great Rift, like the dense region known as the Aquila Rift, are themselves active stellar nurseries. While they block our view of distant wonders, they are busy constructing new ones right in our own neighborhood. The Great Rift, therefore, is a cosmic paradox, a veil that both conceals and creates, reminding us that our perspective is always and forever shaped by the shadows we are born within. Not all dark nebulae are simply black voids. Some wear a faint, ghostly shroud, a reminder that darkness in space is rarely absolute. Drifting through the constellation Orion, not far from the great arc of Barnard's Loop, lies such a phantom, LDN1622. In photographs, it appears as a brooding, complex shape, a jagged mountain range of dust silhouetted against the sky. But what sets it apart is the eerie, ethereal blue glow that clings to its edges like cold foxfire on a log in a deep forest. This is not the nebula itself emitting light, it is a reflection nebula. The dark cloud is being illuminated from the side, likely by one or more nearby hot, young stars. Their intense blue-white starlight scatters off the tiny dust grains on the surface of the cloud, painting its outermost contours with that soft, celestial luminescence. This creates a stunning three-dimensional effect, as if we are seeing a dark cliff face bathed in moonlight. LDN 1622 is remarkably close, only about 500 light-years away, and it is not a heavyweight. Its mass is estimated to be only a few tens of times that of our Sun, making it a relatively modest reservoir of star-forming material. This combination of proximity and low mass makes it a perfect laboratory for studying a specific and mysterious class of celestial objects, brown dwarfs. These are the failed stars of the universe, balls of gas that gathered enough mass to begin collapsing, but never achieved the core temperatures and pressures needed to ignite sustained hydrogen fusion. They occupy the murky boundary between the largest planets and the smallest stars. LDN 1622's conditions seem tailor-made for their formation. The cloud is dense enough to fragment and collapse under its own gravity, but perhaps not massive enough to gather the material required to build a true, shining star. This raises a compelling question: is this dark nebula, with its ghostly blue highlights, currently giving birth to these dim, substellar objects? The presence of the reflection nebula adds another layer of mystery. It tells us that powerful sources of light are nearby, yet the core of the dark cloud remains opaque. What is the exact relationship between the illuminating stars and the dark cloud itself? Are they siblings born from the same larger complex, with the bright stars now accidentally lighting up their dusty cousin? Or is the illumination a chance alignment, a cosmic spotlight that happens to fall upon this particular cloud? The dual nature of LDN 1622, both dark and reflective, makes it a crucial object for understanding a critical transition phase. Astronomers use it to study the precise boundary between a protostellar core, a cold lump of gas destined for collapse, and a protostellar core, one that has already begun forming a central object. By peering into its shrouded heart with infrared and radio telescopes, they can search for the faint warmth of a nascent brown dwarf or a very low-mass star, an ember struggling to ignite within its dusty blanket. This ghostly nebula, then, is a test case for the smallest scales of creation, asking how little material is enough to make something new in the cosmos, and what shadowy forms emerge when a cloud dreams of being a star but falls just short. The ghostly glow of LDN 1622 hints at the delicate interplay between light and shadow, but for a truly riotous display of cosmic color and chaos, look no further than the Rho-Ophiuchi cloud complex. This sprawling celestial masterpiece, a mere 400 light-years away, is the closest major region of active star formation to our solar system. It is a vibrant, tangled canvas where every astronomical process seems to be happening at once. Against the backdrop of the Milky Way's central bulge, the complex is a breathtaking mosaic. Vast swaths of crimson emission nebula glow from hydrogen gas excited by newborn, massive stars. Patches of ethereal blue reflection nebula shimmer where starlight scatters off fine dust like sunlight through a haze. And weaving through it all, an intricate dark spiderweb of dense molecular clouds, the complex's skeletal structure. These are not mere background shadows, they are the active ingredients. The entire scene is dominated by the brilliant multiple star system Rho-Ophiuchi, a group of hot, young suns whose fierce radiation is both illuminating the theater and violently reshaping the set. Their stellar winds carve cavities and compress surrounding gas, while their ultraviolet light sets the surrounding hydrogen ablaze with that characteristic red glow. Yet look closer at those dark lanes. They are not passive. Within their Inkai filaments, the shock waves and pressure from Rho Ophiuchus activity are likely triggering a cascade of new star births. This is the concept of triggered star formation, where the death throes of one generation of stars, or in this case the energetic tantrums of very young ones, create the conditions for the next. A shockwave from a stellar wind slams into a quiet, dark pocket of gas, squeezing it just enough to tip it over the gravitational edge. That pocket collapses, forming a new protostar, whose own birth might then trigger another collapse nearby, like a row of dominoes falling in slow motion through the cloud. This raises a critical question about the entire life cycle of galaxies. Is most star formation a quiet, isolated process, or is it a chain reaction of violence where stars beget more stars through successive waves of creation? The Rho Ophiuchi complex, in all its messy, nearby glory, is our premier laboratory for finding out. Its proximity allows telescopes to resolve incredible detail, peering into those dark lanes to census the newborn stellar population. Astronomers can count how many stars of each mass are forming here, from the brilliant, short-lived giants down to the faint, long-lived red dwarfs. This distribution is known as the initial mass function, a fundamental rulebook for how a cloud of gas parcels out its material into stars. Does a cloud like this always produce the same ratio of massive stars to Sun-like stars to failed brown dwarfs? Or does the chaotic, triggered environment of Rho Ophiuchi skew the results, perhaps producing more of one type than another? By mapping the dark dust and the hidden young stellar objects within it, we are essentially reading the opening chapter of a star cluster's biography, a chapter written in dust and illuminated by the first faint sparks of nuclear fire. This nearby chaos is a mirror held up to our own solar system's origins, asking what violent, colorful nursery our sun was born in so long ago. While the Great Rift splits the southern Milky Way, the northern sky holds its own dramatic tear. High overhead on summer nights, running straight through the heart of the constellation Cygnus the Swan, is a deep, wide channel of blackness known as the Cygnus Rift. Often called the Northern Coalsack, this is no single entity, but a grand tapestry woven from several distinct dark nebulae, including the intricate filaments of Barnard 144 and the sprawling cloud catalogued as LDN 889. Together, they form a ragged curtain that obscures a significant portion of the rich star fields behind them. This positioning creates a stunning celestial diorama. The Cygnus Rift acts as a dramatic foreground silhouette, and what it frames is spectacular. On one side of this dark river, you find the brilliant, gaseous glow of the North American Nebula, its familiar continent-shaped outline seemingly carved out by the adjacent darkness. The dark nebula is not behind the glow, it is in front of it, a closer veil that accentuates the bright nebula's shape by contrast. This raises immediate and practical questions for astronomers trying to map our galactic arm. Just how far away is this dark curtain? Pinpointing the distance to a feature that absorbs light rather than emitting it is notoriously difficult. Current estimates suggest the Cygnus Rift clouds are relatively nearby, perhaps between 1,000 and 2,000 light-years away, placing them within our own Orion spur. But this uncertainty is crucial because it affects our understanding of the mass distribution in our local neighborhood. How much material is actually contained in these obscuring lanes? Is it enough to significantly alter the path of light from more distant objects, or is it a relatively thin, though prominent, screen? The very structure of the rift prompts a deeper mystery. Is this a coherent, physically connected complex, a single vast cloud that has been stretched and sculpted by galactic forces? Or are we simply looking at a chance alignment of several independent, unrelated dark clouds that happen to lie along the same line of sight from Earth, creating the illusion of a continuous rift? The answer lies in their motion. By studying the kinematics of these clouds, measuring their subtle, three-dimensional velocities using radio telescopes, astronomers can determine if they are moving together as a single unit or drifting independently. If they share a common motion, it would suggest a common origin, perhaps the remnant of a single ancient supernova shell or a large-scale gravitational perturbation in our spiral arm. If their motions differ, then the Cygnus Rift is a magnificent cosmic illusion, a layered portrait of unrelated shadows. This investigation does more than solve a puzzle. It provides a key to understanding local galactic dynamics. The motions of these dark clouds trace the flow of interstellar material in our part of the galaxy, revealing the subtle tides and currents that shape the space around our solar system. Is the Cygnus Rift a monolithic structure riding a galactic wave, or a fleeting convergence of dark travelers? Its silent band across the summer Milky Way holds data written in dust waiting to be read. Just 450 light-years away, a quiet revolution is unfolding. The Taurus molecular cloud is the closest major region of star formation to our solar system, a sprawling complex that blankets a huge area of the constellation Taurus. While it is famous for the beautiful, wispy reflection nebulae that grace its edges, its true story is written in shadow. The cloud is crisscrossed by a dense network of dark, filamentary lanes, rivers of dust so thick they completely obscure the light of the stars behind them. These are not mere voids, they are the active construction sites for new solar systems. Unlike the violent, irradiated nurseries of Orion or Carina, Taurus is a place of relative peace. Its star formation is slow, quiet, and remarkably efficient at building one specific type of star, those like our own Sun. Within these dark filaments, astronomers have discovered a population of young stellar objects known as T-Tauri stars. These are suns in their infancy, still contracting under their own gravity and often surrounded by a swirling disk of gas and dust from which planets may one day form. They are the direct precursors to stars like ours, and the dark lanes of Taurus are their cradle. This raises a fundamental question about cosmic diversity. Why is this vast cloud, with enough material to build thousands of stars, producing almost exclusively low-mass, sun-like stars, while other complexes like Orion churn out brilliant, short-lived giants? The answer seems to lie in the cloud's serene environment. Taurus is what astronomers call a quiescent molecular cloud. It lacks the intense radiation and powerful shockwaves from massive O-type stars that dominate other regions. Without that external trigger, star formation here proceeds slowly, driven primarily by the cloud's own internal gravity and turbulence. This slow, gentle collapse favors the fragmentation of the cloud into smaller, denser cores. Imagine a pot of water coming to a boil. In a violent, energetic region, the boil is rapid and chaotic, producing large, bursting bubbles alongside small ones. In Taurus, the heat is turned very low. The water simmers gently, producing a steady stream of small, consistent bubbles. The physics is similar. The slow pace allows smaller condensations to form and collapse under their own weight before they can gather enough material to grow truly massive. Furthermore, the dark filaments themselves provide a clue. Their long, coherent shapes are thought to be sculpted and supported by the cloud's magnetic field. This magnetic scaffolding can slow down the collapse of material even further, preventing a rapid, runaway gathering of gas that would form a high-mass star. Instead, the gas trickles slowly along these magnetic highways, pooling into isolated knots that eventually become individual low-mass stars. So the Taurus dark lanes offer us a vision of a calmer, more methodical path to creation. They prompt us to wonder, was our own Sun born in such a quiet, filamentary dark nebula, slowly coalescing from a dusty thread over millions of years, far from the brilliant chaos of more famous stellar factories? The silent construction ongoing in Taurus may be the most common story of star birth in the galaxy, a story written not in brilliant light but in profound and fruitful darkness. South of the celestial equator, another quiet giant is at work. The Lupus molecular cloud drifts through the constellations of Lupus and Scorpius, a sprawling, fragmented complex of dark nebulae that appears as a patchwork of shadow against the brilliant star clouds of the Milky Way. Unlike the dramatic pillars of Carina or the brilliant chaos of Rho Ophiuchi, Lupus presents a more subtle, mottled appearance. Its darkness is not a single, sharp silhouette, but a collection of ragged voids and dusty lanes, as if the fabric of the galaxy here is threadbare and worn. This modest facade, however, belies its profound importance. The Lupus cloud is one of the nearest regions of ongoing star formation to our Sun, sitting roughly 500 light-years away. Its relative tranquility, much like the Taurus cloud, makes it a perfect observatory for studying the most common outcome of cosmic creation, the birth of small, stable stars and the planetary systems that may accompany them. Within its dark folds, astronomers have identified a rich population of young, low-mass stars, many still enshrouded in the very dust that formed them. But the true treasure of Lupus lies not just in the stars themselves, but in what surrounds them. This cloud has become a premier hunting ground for protoplanetary disks, those swirling, flattened rings of gas and dust that orbit infant suns. Often called proplyds, these disks are the birthplaces of planets. The dark material of the Lupus nebulae provides the raw feedstock for these cosmic construction zones. The discovery of so many proplyds here at various stages of evolution raises a critical question about timing and efficiency. How quickly does a cloud like Lupus convert its dark dust into these planet-forming disks? And how long do the disks themselves survive before dissipating or coalescing into worlds? Observations suggest the star formation rate in Lupus is relatively low and steady, a slow simmer rather than a rapid boil. This gentle pace may be a key factor in the development of complex systems. Without the violent radiation from massive stars to quickly blow away the delicate dust, the proplyds in Lupus might enjoy a longer, more stable period to form the seeds of planets. This leads directly to the core mystery of the cloud's own evolution. Is Lupus a single, coherent complex slowly giving up its material to create stars, or is it a collection of smaller clouds in different stages of their life cycle? Mapping its dark filaments and comparing the ages of its young stars can reveal whether star formation swept through the cloud like a wave, or if it flickered to life independently in isolated pockets. Each dark blotch we see represents a reservoir of possibility, a cache of carbon, silicon, and ice that could one day become the core of a rocky world or the atmosphere of a gas giant. The Lupus molecular cloud, in its quiet southern sky obscurity, is therefore a direct link between the impersonal darkness of interstellar space and the specific, wondrous potential of new solar systems. It compels us to ask within which of these unremarkable dark patches is another Earth currently taking shape, grain by microscopic grain. Deep in the southern sky, a sprawling, fragmented darkness mirrors the quiet work of Lupus. The Chameleon complex is a vast and nearby stellar nursery, so close at just over 500 light-years away that it blankets a huge area near the celestial South Pole. It is not a single entity, but a family of 3 main dark clouds, each named for its position, Chameleon 1, 2, and 3. This complex presents a different face than the dramatic pillars or brilliant clusters we have seen. It is a landscape of subtle textures, a mix of in-sky absorption nebulae that block the starry background, soft blue reflection nebulae where dust scatters the light of embedded young stars, and a few sparse, young open clusters sparkling like delicate jewels sewn into a dark velvet cloth. This environment is crucial because it represents star formation in its most isolated, undisturbed state. Unlike the chaotic nurseries dominated by massive, short-lived O-type stars, Chameleon lacks those brilliant tyrants. There are no overpowering sources of ultraviolet radiation here, no searing stellar winds to violently sculpt and compress the cloud from within. This raises a fundamental question about what starts the process of creation. If there is no external trigger from a nearby giant star going supernova or a powerful shockwave, what exactly causes a quiet, cold cloud like this to suddenly begin collapsing into stars? The answer seems to lie in the cloud's own internal dynamics. The slow, churning motions of turbulence within the dark filaments, combined with the subtle, relentless pull of gravity acting on denser knots, may be the primary architects here. It is a story of spontaneous collapse where the cloud fragments under its own weight, piece by piece, in relative silence. This makes Chameleon a pristine laboratory for studying the very beginnings of a star's life. Within these dark clouds, astronomers have identified a rich population of Class 0 and Class 1 protostars. These are the youngest known stellar objects, mere infants still deeply embedded in their natal cocoons of gas and dust. They are not yet true stars, but glowing balls of contracting material, their warmth detectable only in the infrared and submillimeter wavelengths. Studying them is like having a time machine that takes us back to the first 100,000 years of a solar system's existence. What do these hidden embryos reveal? They show us that the process of gathering material from the surrounding cloud is not smooth or steady. These protostars accumulate mass in fits and bursts, likely as clumps of denser material from the filament fall onto the growing core. Their surrounding disks, the raw material for future planets, are also forming incredibly early, perhaps even as the protostar itself takes shape. The Chameleon complex, in its diffuse and fragmented state, allows us to watch this earliest chapter unfold without the deafening noise of more energetic regions. It prompts us to wonder if our own sun began in such a quiet, isolated fragment of a dark cloud, its birth triggered not by a cataclysm, but by a gentle, gravitational whisper that echoed for eons before the first flicker of fusion finally answered. The quiet, isolated cradles of Taurus and Chameleon show one path to stardom, but sometimes the universe prefers to build in concentrated, dramatic clusters. Just over 400 light-years away, nestled against the border of the small southern constellation Corona Australis, lies a dense knot of cosmic potential. The Corona Australis molecular cloud is one of the closest and most compact star-forming regions we know. Unlike the sprawling, fragmented complexes, this cloud presents a tight, almost jewel-like arrangement of dark and bright nebulae, all wrapped in a distinctive, graceful arc. This curved silhouette against the Milky Way is its most striking feature, a celestial crescent of dust and gas. Within this arc, the interplay of light and shadow is beautifully illustrated by the dynamic region known as NGC 6729. Here, the dark cloud is not just a passive absorber, it is an active participant in a light show. The nebula's appearance changes visibly over just a few years, a rarity in astronomy. Patches of it brighten and fade as variable young stars buried within its heart flicker, their changing light illuminating the surrounding dust like a cosmic lighthouse sweeping through fog. This is a reflection nebula in real time, proving the cloud is not a static sculpture but a vibrant, evolving nursery. The stars being born here are not the monstrous, short-lived giants that dominate other factories. Instead, the Corona Australis cloud specializes in low to intermediate mass stars, bodies similar to or a few times larger than our Sun. Their formation is happening in dense, compact cores deeply embedded within the dark lanes, hidden from optical view but glowing warmly in infrared light. This raises a compelling architectural question. What sculpted the cloud's perfect arc? Such a clean, curved structure in space is rarely an accident. Two leading theories point to violent origins. The first suggests the expanding shockwave from an ancient, nearby supernova could have swept through this region, compressing the gas and dust into this bowed wall, much like snow plowed by a shovel. The second proposes that powerful stellar winds from a previous generation of massive stars, now long gone, could have blown a bubble in the interstellar medium, with the dark cloud representing one surviving, curved segment of the bubble's shell. In either case, the shape itself is a fossil record of past cosmic violence, a shock wave frozen in dust. This compactness is what makes the Corona Australis cloud so valuable to science. Because the entire complex is nearby and its star-forming cores are packed into a small volume, it acts as a concentrated laboratory for studying clustered star formation. Astronomers can observe a whole population of young stellar objects, from faint protostars to visible T-Tauri stars, all at roughly the same distance and born from the same parent cloud. This allows for a direct comparison, letting us ask how subtle differences in a core's initial conditions, like its density or temperature, lead to different stellar outcomes. Does a slightly denser knot-in-the-dark filament always produce a slightly more massive star? The Corona Australis arc, in its beautiful, confined chaos, holds the data to trace that lineage from dark core to shining star, reminding us that even the most serene cosmic curves can be the scars of ancient cataclysms now giving birth to new light. Its graceful arc stands in stark contrast to another southern sentinel, one defined not by curvature but by a stark, linear simplicity. Drifting through the constellation of Musca, just a short distance from the brilliant stars of the Southern Cross, is the Musca dark cloud. This is not a complex tapestry or a sculpted pillar. It is a long, needle-like filament of pure darkness, a slender sliver of cosmic soot that seems to have been drawn with a ruler across the starry background. Its isolation is its most telling feature. Unlike the tangled webs of the Great Rift or the chaotic nurseries of other complexes, the Musca cloud sits relatively alone, a pristine and undisturbed reservoir of cold gas and dust. For astronomers, this simplicity is a gift. The Musca dark cloud is considered a textbook example of an isolated quiescent filament. There are no brilliant, massive stars embedded within it to violently churn its contents, and no obvious external shockwaves are compressing it. This makes it an ideal, almost laboratory-like environment for studying the fundamental chemistry and physics of a molecular cloud in its natural state. By analyzing the faint radio waves emitted by molecules like carbon monoxide deep within its core, scientists can map its temperature, density, and internal motions with exceptional clarity. They are essentially taking the cloud's vital signs, listening to the quiet hum of a cosmic body at rest. This pristine condition, however, raises a profound and puzzling question about cosmic timelines. With so much raw material gathered into one coherent structure, why has the Musca cloud not yet gotten down to the serious business of building stars? Its quiescence suggests it is being held in a state of delicate balance. Several invisible forces may be responsible. Internally, the cloud's own magnetic fields could be providing crucial support, acting like a scaffold of invisible lines that resist gravitational collapse. The gentle, turbulent motions within the filament might also be generating enough outward pressure to counteract the inward pull of its own mass. Externally, the lack of a triggering event, like a nearby supernova shockwave or the intense radiation from a passing massive star, means it has simply been left to its own devices, a sleeping giant in the interstellar medium. This leads to a compelling speculation. Are we looking at a cloud caught in a very early pre-stellar phase? Perhaps the Musca dark cloud represents a chapter that precedes the story we see in places like Taurus or Chameleon. It may be a gathering of material that has reached a critical density but has not yet received or generated the final nudge required to initiate fragmentation and collapse. If that is the case, then this dark needle is a frozen moment of potential, a snapshot of a stellar nursery before the first spark ignites. Its future hangs on a subtle shift in that balance. A chance encounter with another cloud, a ripple from a distant galactic spiral arm, or even the slow, cumulative effect of its own gravity over the next few million years could be the trigger. The Musca dark cloud, in its stark and silent simplicity, asks us to consider the patience of the universe and how long a cloud can dream of becoming stars before that dream finally becomes a fiery reality. These dark, isolated filaments represent a state of cosmic patience, but in other corners of the galaxy, patience is a luxury no cloud can afford. In the southern constellation Centaurus, a brilliant stellar nursery named IC2944, whimsically called the Running Chicken Nebula, glows with fierce, pinkish light from the intense radiation of newborn massive stars. Against this radiant canvas, something strange and defiant is happening. Scattered across the nebula like black tadpoles swimming in a sea of fire are a collection of small, dense, and remarkably dark blobs. These are Thackeray's globules, named for the astronomer who first studied them in detail. They are not part of the glowing gas, they are intruders or perhaps survivors. Each globule is a compact fortress of cold molecular gas and dust, a tiny dark nebula that has wandered into or been caught within a zone of extreme astrophysical violence. The massive stars nearby are pouring out a torrent of ultraviolet radiation and supersonic stellar winds, a continuous onslaught that is slowly boiling away the outer layers of these globules. This process, photoevaporation, is stripping them apart atom by atom, creating the faint, shimmering outlines we sometimes see around them, the last gasp of their material being ionized and swept away. Their tadpole shapes are no accident. The fierce stellar wind is sculpting them, blowing their less dense material into long tails like cosmic comets, pointing directly away from the source of their destruction. This sets up a dramatic, real-time race against annihilation. Inside each dark globule, shielded by its own dusty walls, the intense external pressure from the radiation might actually be compressing the gas, potentially triggering gravitational collapse. This raises a heart-pounding question. Can a star form fast enough inside one of these tiny, besieged fortresses before the fortress itself is completely obliterated? It is a brutal experiment on the limits of star formation. Thackeray's globules are smaller and less massive than the great pillars of creation, meaning they contain limited raw material. The clock is ticking violently fast. Astronomers study them to understand the balance between two titanic forces, the crushing pressure from outside that can spark creation, and the erosive power from that same source that can erase it entirely. Will any of these dark specks manage to ignite a nuclear furnace in their hearts, birthing a star that then helps blow away its own cradle? Or are they simply doomed, destined to be completely evaporated, their material scattered back into the interstellar medium without ever forming a single world? Their struggle, visible in a single telescope frame, captures the precarious and violent nature of cosmic birth, where whether a star lives or dies can depend on a fragile dark blob's resilience against an unimaginable storm of light. The desperate struggle of Thackeray's globules is a small-scale rehearsal for a far grander, more violent performance. To witness star formation pushed to its absolute limit, you must look toward the southern constellation of Carina, home to the largest and brightest nebula in our sky. The Carina Nebula is a cosmic inferno, a vast stellar factory where the most massive and unstable stars in the galaxy are born, live, and die in spectacular explosions. Its brilliance, fueled by titans like the volatile, hypergiant star Eta Carinae, dominates the view, but within that overwhelming radiance, the true architects of the scene are the shadows. Weaving through the glowing gas are immense, brooding pillars and spires of absolute blackness, some stretching for light years. These are not background features, they are the dense, foundational columns of the original molecular cloud, the raw material from which the brilliant stars themselves were forged. They stand as dark fortresses under a continuous, devastating siege. Dozens of massive O-type stars within the nebula bombard these structures with unimaginable levels of ultraviolet radiation and supersonic stellar winds. The visible edges of the pillars glow with a fierce, ionized rim, a shock front where the cloud's material is being violently boiled away into space. This process is eroding the pillars at a phenomenal rate, stripping away entire solar masses of material every million years. Yet their persistence is the central mystery. How can such delicate-looking structures withstand this astrophysical hurricane? Their survival is a testament to their incredible initial density. These are not wispy clouds, but the densest knots of the original cloud, packed so tightly with gas and dust that gravity and internal pressure hold them together against the external onslaught, at least for a time. This sets the stage for a profound paradox. The very forces that are destroying these pillars may also be triggering new creation deep within their shielded hearts. As the intense radiation and winds compress the pillars from the outside, the pressure can squeeze internal pockets of gas past the point of gravitational collapse. This means that while the outer layers of a pillar are being scoured away, the inner sanctum might be collapsing to form a new generation of stars. These would be second-generation stars, born from the ashes of the cloud that created the very monsters now trying to tear it apart. Infrared telescopes have indeed peered through the dust, revealing the faint warmth of protostellar objects embedded within several of Carina's dark pillars. This raises a staggering question about cosmic timescales and efficiency. Can a star form, ignite, and begin shining before its protective dusty cradle is completely evaporated by the stellar fury that helped create it? The pillars of Carina are the ultimate crucible for this test, a place where the cycle of creation and destruction is accelerated to a blinding, violent speed. They are monuments to both endurance and transience, asking us what fragile new worlds might be taking shape in the brief, dark calm at the center of a storm that spans light years. The Carina Nebula's violent crucible shows creation under siege, but not all stellar nurseries announce their presence with such ferocious light. Spanning the border between the constellations Monoceros and Canis Major is a vast, faint emission nebula known as IC 2177, or more poetically, the Seagull Nebula. From a distance, its broad, sweeping arcs of glowing hydrogen gas do indeed suggest the outspread wings of a great bird in flight. Yet what gives this celestial seagull its form, its texture, and its sense of depth are not the bright gases, but the intricate network of dark dust lanes that vein through it. These are not mere background shadows, they are the nebula's skeleton. The dark, ragged filaments carve the glowing gas into distinct regions, creating the illusion of layered feathers and giving the wings their defined structural appearance. Without this intricate embroidery of darkness, the seagull would be little more than a shapeless, luminous fog. These dark lanes are far more than cosmetic. They are dense rivers of cold gas and dust, the raw material from which the nebula's stars are born. The entire Seagull complex is a site of ongoing, though not overwhelmingly violent, star formation. The bright glow of the nebula is powered by young, hot stars embedded within it, their ultraviolet radiation exciting the surrounding hydrogen. But the dark dust lanes tell a story of what came before and what is still to come. They represent the remnants of the original molecular cloud that fragmented to create those stars. Their twisting paths trace where material is most concentrated and where gravity may yet win out to collapse new pockets into future suns. This raises a subtle question about the nebula's life cycle. Are we seeing a single, coherent event or multiple generations of star birth? The pattern of the dark lanes suggests a complex history. Some may be pristine, undisturbed filaments yet to form stars. Others might be the hollowed-out shells around stellar clusters that have already blown clear cavities in the cloud, their dark walls now illuminated from within. The true puzzle of the Seagull lies in disentangling its geometry. When we look at this beautiful winged shape, are we seeing separate, unrelated dark clouds that just happen to line up along our view, creating a layered silhouette? Or are these dark lanes physically connected, like the roots of a great tree, all part of one vast, interconnected complex that stretches deep into space? Astronomers use tools like precise distance measurements and studies of the dust's motion to answer this. If the dark structures are at different distances, the nebula's unified shape is a magnificent illusion of perspective. If they are connected, then the seagull is a single, enormous entity being sculpted by the stars it birthed. This distinction changes everything about how we understand the forces at work. Interconnected tendrils would mean that energy and shock waves from star formation in one wing could travel along these dark channels to trigger collapse in another, creating a chain reaction of starbirth across the structure. Furthermore, these dark dust lanes act as cosmic channels and barriers for the very radiation that makes the nebula glow. They can shield pockets of gas from the intense ultraviolet light, allowing them to remain cool and dense enough for gravity to act. Conversely, they can also funnel that radiation down specific corridors, intensifying its erosive power and sculpting the bright gas into sharp ridges. This creates a dynamic feedback loop. The dark dust defines where stars can form by providing shielded nurseries, and then the stars that are born immediately begin to destroy and reshape the dark dust that created them, carving new lanes and pillars with their light. So within the graceful wings of the seagull, a quiet, persistent drama unfolds. Which of these dark veins currently hides a stellar embryo, and which are simply ghostly outlines of structures already spent? The nebula's serene beauty masks a deep architectural mystery, asking us to see not just a bird in the sky, but the hidden scaffolding that holds it together, and the silent, dusty cradles that may one day set its wings ablaze with new light. Our journey through the Milky Way's shadows reveals a pattern, but is it a universal rule? To find out, we must step outside our own galaxy and look toward a faint, wispy cloud in the southern sky, the Large Magellanic Cloud. This is not a true nebula within our galaxy, but an entire satellite galaxy, a separate island of stars, gas, and dust orbiting our own, and within its sprawling, chaotic arms, dark nebulae are at work. We can see them, inky blotches against the LMC's bright star-forming regions, proving these cosmic nurseries are not unique to the Milky Way. One of the most striking is a complex known as N159, a vast, turbulent region where dark dust lanes carve through glowing gas with a familiar yet alien architecture. This immediately challenges a fundamental assumption. The Large Magellanic Cloud has what astronomers call a lower metallicity. This simply means it contains fewer heavy elements, things like carbon, silicon, and iron, than our own galaxy. These are the very elements that form the dust grains in dark nebulae. So the dust in N159 is different. It is more primitive, composed of a simpler blend of materials, likely richer in simpler compounds and ices. This difference in raw ingredients raises two profound and connected questions that shake the foundations of our local knowledge. First, how does star formation proceed inside an extragalactic dark cloud like this? Our best models of how clouds collapse, fragment, and ignite are built on detailed observations of nebulae right here in our galactic neighborhood. But if the recipe for the dust itself is different, does the entire cooking process change? The dust in a cloud plays a critical role in cooling it. As a cloud collapses, it heats up. Dust grains radiate that heat away as infrared light, allowing the cloud to continue condensing. If the grains in the LMC are made of different stuff, do they cool the cloud as efficiently? This could alter the minimum mass needed for a cloud fragment to collapse, potentially changing the sizes of the stars that form. Second, and even more intriguing, does this different dust composition directly affect the types of stars that are born? In our galaxy, we see a certain distribution, a predictable mix of red dwarfs, sun-like stars, and brilliant giants. Is that mix the same in the Large Magellanic Cloud? Some evidence suggests it may not be. The LMC seems to form massive, luminous stars at a higher rate relative to small ones than the Milky Way does. Could the nature of its dark nebulae be a reason why? Perhaps with simpler dust, the early stages of collapse are less efficient at breaking the cloud into small fragments, leading to more massive condensations. Or perhaps the entire life cycle of the cloud is accelerated. Observing dark nebulae like N159 is our only way to test these ideas. We are no longer just studying cosmic structures. We are conducting a galactic-scale experiment, comparing two separate laboratories with different initial conditions. The dark lanes in the Large Magellanic Cloud are a mirror held up to our own galaxy's processes, but it is a mirror in a different room under different light. They force us to ask whether what we have learned at home is a universal truth or merely a local custom. The universe's rules seem to break down at the very heart of our galaxy. There, in the chaotic maelstrom surrounding the supermassive black hole, lies one of the most stubbornly mysterious dark clouds ever discovered. Catalogued with the unassuming name G 0.253 plus 0.016, astronomers simply call it the Brick. This is not a poetic nickname for its shape, but a blunt description of its nature. It is a colossal, monolithic slab of cold gas and dust, so incredibly dense that it appears as a void of nothingness, not just in visible light, but even in the mid-infrared wavelengths that usually pierce through cosmic soot. Imagine a cloud so thick it swallows even the heat signature of its own dust. That is the Brick. Its statistics are staggering. Located a mere 100 light-years from the Galactic Center, it contains over 100,000 times the mass of our Sun packed into a region just 30 light-years across. By every standard metric we have developed from studying quieter nurseries like Taurus, this cloud should be a frenzied fireworks factory. With that much mass compressed into that small a volume, gravity should have won decisively by now, triggering a spectacular burst of massive star formation. Yet, when astronomers point their most powerful radio and infrared telescopes at it, they find a profound and puzzling silence. The Brick shows only the faintest, most tentative hints of stellar embryos. It is a cosmic warehouse packed to the rafters with star-making material, but the lights are off and the machines are still. This contradiction places it directly at the center of a major astronomical mystery. What powerful force is holding the doors shut, preventing gravity from turning this vast reservoir into stars? The leading suspect is the cloud's unimaginable environment. The Galactic Center is a realm of extremes. The gas there is subjected to intense tidal forces from the black hole's gravity, fierce radiation from countless neighboring stars, and supersonic turbulence that churns the interstellar medium into a froth. The Brick itself is likely crisscrossed by powerful magnetic fields, creating an invisible internal scaffold that provides support against collapse. It is possible that the cloud is so turbulent internally, with gas motions so violent and chaotic that the particles simply cannot settle down enough to coalesce under their own weight. Think of trying to build a house of cards in the middle of a hurricane. The pieces are all there, but the environment is too chaotic to allow them to snap together. Another, more dramatic possibility is that we are catching the Brick at a very special moment. Perhaps it is not a failed star former, but a pre-stellar cloud on the very brink. Some theories suggest that clouds in such a harsh environment may need to accumulate an extraordinary amount of mass before they can overcome the external pressures trying to tear them apart. The Brick might be gathering itself, building up to a single, monumental burst of creation that will flood the Galactic Center with new stars all at once. Or its fate may be more tragic. The extreme forces at the galaxy's heart might simply tear it apart before it ever gets a chance to ignite, scattering its precious material back into the void. The Brick stands as a stark challenge to our understanding. It forces astronomers to ask if the quiet, slow-motion star formation we see in our galactic suburbs is the exception, not the rule. In the universe's most crowded and violent downtown, the rules of construction may be written in a language we are only beginning to decipher. What does this dark, silent Brick tell us about the harsh realities of building stars in a cosmic metropolis? The silent enigma of the Brick is not a solitary oddity. It is part of an entire hidden population of cosmic giants, so dense and cold they are invisible not just to our eyes but to most of our telescopes. To find them, we must look at the galaxy in a fundamentally different light, the infrared. Scattered along the Milky Way's spiral arms are ragged, inky silhouettes seen only against the warm, glowing backdrop of interstellar dust. These are infrared dark clouds, or IRDCs, and they are the ultimate vaults of star-making material. Their nicknames, born from the shapes our minds impose on their blotchy forms, hint at their mystery: the tadpole, the caterpillar, and a pair known as the mice. These are not the dark nebulae of constellation lore. They are far more extreme. IRDCs are the coldest places in the galaxy, with temperatures plummeting to just 10 to 20 degrees above absolute zero. They are also phenomenally dense, packing the mass of thousands of suns into regions often less than a few light years across. Their darkness in the infrared is the key clue. The galactic plane itself glows with the faint warmth of countless dust grains heated by starlight. An IRDC is a cloud so thick and frigid that it absorbs even this background infrared glow, appearing as a stark black hole in the infrared sky. This profound opacity signals something monumental. Within these lightless vaults, gravity operates with near-total control, free from the disruptive influence of external radiation or heat. This makes them the prime suspects for a very specific cosmic crime: the birth of the galaxy's most massive and rarest stars. While sun-like stars may form in the quieter filaments of Taurus, astronomers believe the monstrous O-type stars, behemoths dozens of times heavier than our sun and shining with 1,000,000 times its brilliance, are forged in the crushing, secret depths of IRDCs. This belief, however, opens a canyon of unanswered questions. The process of high-mass star formation remains one of the great unsolved puzzles in astrophysics. We understand the slow collapse that builds a star like our own, but how does a cloud manage to gather and funnel such an enormous amount of material onto a single core without it fragmenting into many smaller stars? The internal dynamics of an infrared dark cloud must hold the secret. Their incredible density suggests they are not peaceful places. Radio observations reveal they are seething with supersonic turbulence, a chaotic churning of gas that could prevent widespread fragmentation, allowing only a few privileged cores to rapidly accrete most of the cloud's mass. Furthermore, their shapes, those jagged, filamentary structures, may act as cosmic rivers, funneling material from vast distances down into a few dense hubs, like streams feeding a deep lake. What are the exact initial conditions within a cloud like the mice that allow this runaway accretion to begin? Is there a critical density threshold or a specific configuration of magnetic fields that tips the balance from forming a cluster of small stars to birthing a single brilliant titan? We cannot see inside. Their very nature, which makes them perfect stellar wombs, also makes them perfect obscuring veils. Each of these infrared shadows is a locked room, and inside, the universe is conducting its most ambitious and violent experiments in creation. What we learn by studying their cold, dark outlines may finally reveal how the brightest lights in the cosmos are born from the deepest darkness. This final dark nebula redefines the very concept of a shadow in space. It is called Maggie, and for decades it was completely invisible. Discovered only recently, Maggie is not a blot that blocks starlight, nor does it glow with the heat of dust. Instead, it is a filament of pure, cold, atomic hydrogen gas, a river of the most basic element in the universe, stretching for an almost unimaginable 3,900 light-years. To put that in perspective, if you placed it between our solar system and the nearest major galaxy, the Andromeda Galaxy, it would span nearly a tenth of the entire distance. This is not a cloud, it is a cosmic artery. Astronomers found it not by seeing darkness, but by listening to a very specific whisper. They used radio telescopes to detect the faint spectral line emitted when the spin of an electron in a hydrogen atom flips. This signal revealed a structure so vast and coherent it defied belief. But the true shock came when they mapped its orientation. Maggie aligns almost perfectly with the Milky Way's magnetic field. This is not a chance alignment. It suggests the galaxy's invisible magnetic scaffold is actively guiding and shaping this colossal stream, holding it together across distances that dwarf entire star clusters. This discovery shatters our previous models. We thought the interstellar medium was a chaotic soup where gas clumped into clouds that then formed stars. Maggie suggests a grander, more organized architecture. It appears to be a primordial thread, a fundamental backbone from which the galaxy's structure may be woven. This raises two groundbreaking questions that cut to the heart of cosmic evolution. First, is Maggie a direct precursor to a giant molecular cloud? Is this how the raw hydrogen, scattered after the Big Bang, is first gathered into the immense reservoirs needed for star formation? The theory is stunning. Atomic hydrogen, guided by magnetic fields, flows along these vast filaments. Where filaments cross or not, the gas density increases, hydrogen atoms pair up to form molecules, and a dark molecular cloud is born. Maggie could be the missing link, showing us the universe's method for building its star factories from the ground up. Second, and more profound, how does something so enormous and delicate maintain its coherence? What prevents it from dissipating into the void or fragmenting under its own turbulent motions? The answer seems to lie in that magnetic alignment. The field lines may act like rails on a cosmic scale, channeling the flow and providing a skeleton that resists disruption. This presents a new paradigm where magnetism is not just a minor player, but a master architect sketching the blueprints for galactic structure with lines of force before a single star ignites. Maggie is more than an object. It is a question written across the sky. It asks us to reconsider how emptiness becomes something, and how the largest structures in a galaxy begin not with a bang, but with a whisper, a slow, magnetic gathering of the most basic stuff of existence into a river of potential, waiting for gravity to find it. From the familiar Coalsack beside the Southern Cross to the magnetic river Maggie stretching thousands of light years, our journey through 25 dark nebulae has revealed a universe painted in shadow. We have seen these cosmic inkblots as more than mere holes in the starry fabric. They are dynamic characters in an epic story of creation and destruction. Each one, from the besieged pillars of Carina to the silent enigma of the brick, raises profound questions that challenge our understanding of the cosmos. How does a cloud decide to become a star? What invisible forces of magnetism and turbulence sculpt these dark forms? And how do the violent, brilliant stars they birth ultimately turn and destroy their own cradles? The answers are not written in light, but in the intricate architecture of the dust itself. These 25 shadows are not a complete catalogue, but a curated collection of cosmic mysteries, each a unique puzzle piece. The delicate filaments of Taurus teach us about the quiet birth of suns, while the infrared dark clouds hint at the violent forging of stellar giants. The Great Rift obscures our galactic center even as it creates new stars within its own dark folds. Every patch of darkness you see in the Milky Way is a sentence in a story we are still learning to read. So the next time you find yourself under a truly dark sky, look up, trace the ragged path of the Milky Way, and let your eyes settle on those patches of nothingness. See the Coalsack, the pipe, the Great Rift. Do not see them as voids. See them as question marks written in dust, as active construction sites and ancient fossils, as the hidden engines of galactic evolution. Each one is a mystery waiting for its story to be told. Which of these 25 cosmic shadows intrigued you the most? Was it the fleeting beauty of the Horsehead, the silent potential of Barnard 68, or the violent paradox of the Carina pillars? Share your thoughts in the comments below, and if you enjoyed this journey into the darkness, subscribe for more explorations of the universe's deepest mysteries. The night sky is full of stories, and the darkest chapters are often the most